7.2 is talking about transformations of graphs. Okay, one thing you're going to want to keep in mind in 7.2 are the shapes of what we consider to be our basic graphs. Some people or books call these our parent graphs. They're ones that are fairly common and we'll see over and over again. We have the squaring function, which is x squared. Anybody remember what the name of that shape of a graph is? Is it a line? No, it's a parabola. Excellent. Then we have the cubing function, which is x cubed. It kind of looks, some people call that a ziggy graph, but it kind of looks like a sideways Z. We have the square root function, the absolute value function, which is typically identifiable by the V in there, and then we have a cube root function as well as a one of our parent functions or our basic graphs. Most of the graphs that we do as far as translations in this section are going to be translations or movements of these basic graphs. Okay, and if you have a graphing utility or if you're using one on your computer, you can always pull up a graph of the basic function. But what we're going to do is we're going to pick up these basic functions and we're going to move them right or left or up or down, or maybe we're going to make them taller or shorter. We're going to adjust what the originals look like. So just for a moment, I'm going to pull out a graphing calculator here, and I am going to graph y equals x squared. So I'm just going to use the first basic function as my guide here. And then on the next one, I'm going to graph x squared plus 2. And then on the third line, I'm going to graph x squared. Sorry, let me see if I can make that a little bit. If I put that too close to the light, it will be really glary. All right, so the third one, I'm going to graph x squared minus 3. Okay, so if I just graph those, I'm going to zoom 6 so we have the standard viewing window. Here comes my first graph, the basic parabola x squared. Here's my second graph, the x squared plus 2. And my third graph, the graph of x squared minus 3. Notice all those graphs are the same basic shape. But if the blue graph or that middle graph was our original, when I graphed x squared plus 2, what did it do? Well, it just picked the graph up and moved it up 2 units. When I graphed x squared minus 3, it picked the graph up and moved it down 3 units. This is what we call a vertical translation, and that is achieved when you add or subtract a constant outside of your basic function. So if you have a basic function f of x, in our case it was x squared, but if you add a number outside that basic function, it's going to shift the original function up that many units. If you subtract a number outside the basic function, it will shift the function down that many units. Okay? Now, what if instead of, let me find the sweet spot as far as the glare is concerned. Okay, what if instead of adding or subtracting outside the function, I added or subtracted inside the function with the x? So instead of doing x squared plus 2, I'm going to do x plus 2 squared. Instead of doing x squared minus 3, I'm going to do x minus 3 squared. Whoops, except I have a whole lot of extra stuff out there, don't I? Okay, so I'm not adding outside the function or subtracting outside the function. I'm adding or subtracting inside with the x. If I graph those three, here comes my original again. then when I graph the x plus 2 squared or the x minus 3 squared, they're all on the same vertical level. This just moves it right or left. Now notice when I added 2 inside, that made us move left 2 units. When I subtracted 3, it made us move right 3 units. In other words, if you replace the x inside one of your basic functions with x minus d, it's going to shift d units to the right. If you replace x with x plus d inside your basic function, it's going to move it d units to the left. These are what we call vertical and horizontal translations. Okay? So, if we had the graph of g of x equals x squared minus 6, and the instructions are graph the following, and before you do that, describe how each graph can be obtained from one of the basic graphs shown earlier. So first thing we want to do is identify what is our basic graph here. On x squared minus 6, the basic graph is f of x equals x squared. Okay, so when we're talking about the basic graphs, we're looking for either an x squared or a cube or an absolute value, something from that parent graph list. Now, is this minus 6 inside the squaring or outside the squaring? Outside, exactly. So this is an outside movement. In other words, it's not inside with the x, so that's going to be a vertical shift. When you subtract a number, it's going to move it down. So this moves the graph of x squared down 6 units. Okay, so if we looked at the graph of x squared, which has the parabola 0, 0, let's see, we would have, what, 3, 9. Hang on, I have to sneeze. I'm so sorry. Okay, so here's my parabola. This is just plain old x squared. So if I want to graph x squared minus 6, I'm going to pick every point on that graph up and move it down 6 units. So where it was at 0, 0, the new y value will be negative 6. Where it was at 9, the new value will be 3. 9 will go to 3. So my new graph will be here. Same shape, just move down. Is everybody okay so far? All right. Yes. Okay. I think they're already there. Maybe I didn't turn them on, but I did put them there. Yes. I'm so sorry. I'll make sure that I must not have turned them on. You know, sometimes when I actually post something in Canvas, I have to publish it. I may have forgotten to publish that. I'm so sorry. But yes, I will definitely post them. All right. You bet. So what about this one? What is our parent graph or our basic graph here? Well, here we're taking the absolute value of something. So our parent or basic graph will be y equals the absolute value of x. And since we are adding or subtracting inside that basic function, rather than moving the graph up or down, this will move it right or left. When you subtract a constant from x in the original, that's going to move the graph right 4 units. Okay, so our original graph just looks like this. So that's the absolute value of x. And we want to pick up every point on that graph and move it 4 units to the right. So this point will come 4 units to the right. This one, they all will. And our graph will have the exact same shape, just moved over to the right. And it does help if you can draw a straight line. Okay. All right, so I want you guys to try this one. I want you to tell me what is the basic graph, and how you can get this graph from your basic graph. What are you doing to the basic graph to come up with the new graph? So I'll give you a couple minutes to think about that and write it down, and then we will compare. Bless you. Whenever you're ready to compare, just say ready or yes in the chat or whatever, and then we'll compare. It's this one. It's half of a sideways parabola, yes. You're welcome. All right, so in this one, our basic graph is the square root of x. And since we are adding or subtracting inside the basic graph, that's going to move it right or left. Since we added 2, this moves the graph. So that moves the graph of square root of x left 2 units. So if our original graph looks like this, then our new graph will just move 2 units to the left and look like this. Okay. Now that is not linear. My y values on the y-axis are just so close together, it's hard to make it curvy there. For the original one, you start at 0, 0, and so since we moved that graph left 2 units, oh, that's okay, but that's an excellent question. Whatever the original graph starts at, or the points on the original graph, you just have to move them all left 2 units. Now, you can do multiple translations in one. For example, this one, we're talking about still the basic graph here is the square root of x, but we have an addition inside the original and outside. So this is going to move the graph of the square root of x, left 2 from the 2 inside, and down 3. The 2 is inside the basic function, so that's the horizontal movement, and the 3 is outside the basic function, which is the vertical movement. So if we start with our square root function, let's see, this would be 9, 3, would be about here. So there's our square root function. We're going to move every point on there left 2 and down 3. So I'm going to take this point 0, 0, and I'm going to go left 2 and down 3. So that point will be right here. Should have made bigger graph paper. Okay, the point 4, 2 is going to go left 2 and down 3. 9, 3 is going to go left 2 and down 3. So our graph will be the same basic shape, but it's moved left 2 and down 3. I want bigger graph paper. So those are horizontal and vertical translations, and they will always occur when you add or subtract a constant either outside a basic function or inside. If it's outside, it moves the graph up and down, up or down, I should say, and if it's inside, it moves the graph either left or right. All right, we can also do what we call reflections. If you look, for example, at the graph of, say, let's go with absolute value of x, because we may not have seen where you find that on your calculator. Okay. If I want the absolute value, I'm going to go to, still trying to find the sweet spot for the no glare. That's not too bad. I'm going to go to Math, arrow over to Num for the number menu. That very first row up there says ABS. That means absolute value. Okay. So if I do number 1, I'm going to take the absolute value of x. That is my basic function. And on the next one, I'm going to take the negative of that absolute value. Okay, so I took a basic function and then I took the negative of it. Here comes my original absolute value function. And now the red graph, or the second graph graphed, is the negative of it. Let me refocus there. That's just not going to be very good there. Maybe a little better down here. So our original function was the absolute value, and this would be the negative of the absolute value. What did that do? It just took it and took the mirror image of it across the x-axis, or we say that that is a reflection across the x-axis. Anytime you take the negative of a function, wherever the y values were positive, now they're negative. If they were negative, then now they would be positive. So that just flips the points across the x-axis. And in a similar idea, if you replace x with negative x instead of putting the negative in front of the y value, that's going to reflect across the y-axis. So for example, if you had y equals the square root of x as your basic function, which looks something like that, then y equals the square root of negative x will be this graph mirror imaged across the y-axis. So instead of pointing this way, it will flip over and go this way. Those are our reflections. So if you have, for example, negative the square root of x plus 2, what would be our basic graph here? Well, our basic or parent graph would be the square root of x, and we're doing two things to it. The plus 2, that's going to move it left 2 units, and the negative sign in front, that's going to reflect across the x-axis. So this takes the basic graph of square root of x and does a left 2 units and x-axis reflection. So if your basic graph looks like this, we're going to go left 2 to start. So that graph, the purple one, would just be the square root of x plus 2. And then every y value, we're going to take the negative of it. This point, since the y value is 0, it won't change. Here, if the y value is 2, it will become negative 2. Where the y value is 3, it will become negative 3. So it just takes that graph and reflects it, mirror image, across the x-axis. So it's going to look like this. Questions so far? All right, we already did this one. I mean, I just did that one as an example up there. But yeah, if you have the square root of x, taking the square root of negative x just takes the x values and flips them across the y-axis. I should have looked down before I did that example. All right, so we can, at this point, move the graph right or left, up or down, and we can cause it to have a mirror image across the x or y axis. We can also make graphs taller or shorter, or narrower or wider. Those are caused by multiplying either inside or outside of a function with a constant. For example, let's say we have, what's one we haven't used? Maybe x cubed. Okay, so let's say we have x cubed as our basic graph. Okay. And I am going to do, say, 3x cubed as my second graph, and I'm going to do, say, 0.2 x cubed as my third graph. Okay. So if I graph those, let me try no light here for just a second to try to get rid of, well, that just made that glare way worse, didn't it? All right, so let me get back over here. Okay, so if I graph my original graph, here comes y equals x cubed. That's just our basic graph. Second graph is going to be the multiple by 3. And the third graph is going to be the multiple by 0.2. Notice the shapes are all basically the same shape. But if you look at a particular x value, say let's look at this x value. For the original graph, the y value is right here. But for the multiple by 3, it's way up here. And for the multiple by 0.2, it's further below. This is what, yes? So what happens is when you multiply by a constant that's higher than 1 or bigger than 1 outside of your basic function, it basically makes the graph taller. Or in other words, it stretches it vertically. When you multiply by a number that's less than 1 outside the basic function, it's going to make it shorter, or it's going to shrink it vertically. So if you take your basic function of f of x and multiply by a constant, it's going to be what we call either a vertical shrink or a vertical stretch. And that depends on how big the a value is. If the a value has absolute value bigger than 1, it's going to be a vertical stretch. And if the a value has absolute value between 0 and 1, it's going to be a vertical shrink. In other words, this is going to make it taller, and this will make it shorter. Okay. Now, on the same kind of idea, if you multiply inside with a constant, where you multiply the x by a constant, it makes it either wider or narrower. So for example, if you have something like y equals x squared, as your basic graph, if you graphed y equals 2x squared, in other words, I am multiplying the x inside the function by 2, that's going to make it narrower. If I take y equals, let's say, 1/2 x all squared, that's going to make it wider. These are what we call horizontal shrinks or stretches. Notice that when the number that I multiplied by x had absolute value bigger than 1, it made it narrower, so we call that a horizontal shrink. If I multiplied by a number that was less than 1 inside with the x, that made the graph wider, and that's what we call a horizontal stretch. Now notice, if you look at this graph, this is a horizontal shrink. And we call it a horizontal shrink because the multiple of 2 is inside with the x. But you could actually simplify that function and write that as 4 times x squared. Those are the same graph, right? I just squared 2x. If we wrote it this way, now the 4 is in front of the basic function, and since that number is bigger than 1, that is what we also call a vertical stretch. So in other words, a vertical stretch is the same thing really as a horizontal shrink, and vice versa. How do you know which one you're talking about? It depends on where they put the constant. If they put it inside the basic function with the x, then they're going to call it a horizontal shrink or stretch. If they put it outside the basic function, in other words, they factored it out, then that's going to be a vertical shrink or stretch. So for example, if you had y equals the square root of 1/9 times x, your basic function would be the square root of x. The way I have this constant written, it's inside the basic function multiplied by the x. So that will be a horizontal stretch. Okay. If instead I wrote this function as 1/3 times the square root of x, which we could because the square root of 1/9 is 1/3. If I wrote that constant out here, that would be a vertical shrink. These are the exact same function. Whether you identify as a horizontal stretch or a vertical shrink depends on where the constant is written. If it's inside the original function, it's horizontal shrink or stretch. If it's outside, it's vertical. Questions? Did I give you guys enough time to get this written down? Okay. And I will, I'm sorry, I will post those and get that turned on. I don't know what I did. I obviously didn't turn it on right or didn't save it or something, but I will get those up there for you today. Alrighty. All right, so let's try a few examples, and these are just examples out of your homework, okay? So it says, describe how the graph of the following function can be obtained from one of the basic graphs. Okay, so first of all, let's identify what is your basic graph. Yes, absolutely. It's just a basic graph of x squared, which is a parabola. Yes, excellent. Now, what are we doing to the graph of x squared? Well, in this case, we're doing three things. We're adding 2 inside, we're multiplying by 1/3 outside, and we're also multiplying by a negative sign. Okay, so we've got three things going on. So how can it be obtained? Okay, we're going to do what's inside the parentheses first. So this would moves the graph, okay, I'm going to say g of x just to be clear. So g of x moves the graph of x squared left 2 units, because adding 2 to the x moves it left. Since this constant multiple is outside the basic graph, it is going to do a vertical shrink so it vertically shrinks the graph by a factor of 1/3. And how'd I get that factor of 1/3? That's just what I'm multiplying by. And then it also reflects it across the x-axis. So this one has quite a bit going on. We're not doing just 1 or 2 translations. We're actually doing 3. Just take them piece by piece, though. Okay? Any questions about that one? Some of them you will want to graph it. This one they didn't ask. They just asked you to describe how it can be obtained from the graph of the basic function. All right, so what about this one? They even tell us what the basic graph is here. They're telling us that the graph, describe how the graph of g of x equals 1 over x plus 3 and then minus 4 can be obtained from the graph of f of x equals 1 over x. So they're telling us that this is our basic or parent function. So if we look at this one, we have replaced x with x plus 3. In other words, we're adding 3 inside the function. So remember, that's a horizontal movement, and then we're subtracting 4 outside the function, which is a vertical movement. So g of x moves the basic graph, adding 3 inside with the x is going to move it left 3 units and then down 4 units. Everybody okay? All right, I want you guys to try one for me. Okay, so I want you to describe how the graph of g of x equals 2 times the square root of x minus 3 plus 5 can be obtained from the graph of the square root of x. So, and if you want to, just to save a little space over here, we're just going to list the differences. Okay, so we're going to take the square root of x and we're going to do some stuff to it to get this graph of g of x. So I want you to write down what is being done to the graph of f of x to obtain the graph of g of x. And when you're done, just write ready or done or whatever in the chat box and we'll know we can start. All right, we're starting to get some done, so let's think about this together. Our basic graph was the square root of x, so let's start inside the original grouping symbol. So we'll have the square root of x, and we're subtracting 3 inside there. That moves the graph which direction? Right 3 units. Good. Then we multiply outside the original function by 2. That is a, in this case, it'll be a vertical stretch. Since it's called a vertical stretch, if it is bigger than 1, it's going to be a stretch. If it's smaller than 1 in size, it will be a shrink. So this will be a vertical stretch by a factor of 2. And then what does this plus 5 out here do? Yes, and it moves it up 5 units. Perfect. So oh, okay. I just do it in the order that it occurred is why I listed them in that order. And I think in most of the homework problems, they'll actually kind of guide you through what order they want you to list them in. But it does matter in some instances which ones you do first. This one, we're fine. I mean, you know, either way. But sometimes if you're moving left or right and then doing a reflection, you need to be careful about your order. So But actually the order of operations, you do what's inside the parentheses, or so to speak, this guy first, and then you do multiplication before addition. So that's why I was listing it in this order. But they will, in the homework, they'll, kind of give you, it's a fill in the blank a lot of times. And so they'll, kind of be specific about which box they want you to fill in next. Alrighty. So what if we go back the other way? What if they give us a basic function and then ask us to write an equation that does a certain thing to that basic function? So we want to take the square root of x and we want to shift it left 4 units and up 9 units. Okay, so I'm going to call it g of x. My basic function is the absolute value of x, but I want to shift left 4 units. So I'm going to add 4 inside with the x, that's horizontal movement, and then I want to go up 9 units, so that's going to be outside the basic function. So what about find a function that, let's see, the basic shape of y equals x squared is moved right 2 units, reflected across the x-axis, and moved down 4 units. Okay, so we would have our g of x here. We're going to start with something squared. We're going to first of all move it right 2 units. So inside with my x, I'm going to put an x minus 2. That moves it right 2 units. I want to reflect it across the x-axis. So I'm going to take the negative of that, and then I'm going to move it down 4 units. Right, reflection, down. Is everybody okay with that? Yes. Yes, that would be a reflection across the y-axis. Yes. Excellent. All right, there are instances where they won't give us a basic graph. They're going to give us a picture of a graph. Okay? And so what we're going to do is we're going to shift this graph according to whatever they ask us to do. But I don't have a formula for the graph. I just have a picture. Okay, so I'm going to try to focus in and get this just a little bit bigger here. All right. All right. So this is my basic graph. So they identify some key points. Hang on just one second. They have the point negative 5, 0. They have the point negative 2, 2. 0, 0, 2, negative 4, and 4, 0 are kind of the key points that they identified for us. So this part of the graph kind of looks like a shifted and upside down absolute value. We've just got a nice little V here. And this guy kind of looks like part of a parabola, right? So we don't actually have a formula for that graph. We're just going to use that function and either shift it or stretch it or shrink it or whatever they tell us to do. Okay, go ahead. This would probably be a piecewise defined function. Yes. Yes. I don't remember which section it was, but we did, I want to say they were on your test. I just can't remember the section number. I'd have to look back. Okay. But yes, we have done piecewise functions. So, well, it could be defined by a piecewise defined function, yes. Yes. All right. So they've just given us some arbitrary function, and we want to graph 2 times that function. What happens when you take 2 times a function? This is a vertical stretch by a factor of 2. Now remember, when you're talking about graphically, the f of x, remember that's just your y value of a point on the graph. So all we're really saying here is you want to take the y values of the given function and you want to multiply them by 2. It doesn't shift it left or right or anything like that. I'm just making it taller, so to speak, in this case. What happens when I multiply the y value of this point by 2? Well, when I multiply 0 by 2, I still get 0, right? But what about when I multiply the y value of this point by 2? Well, when I have the point negative 2, 2, if I multiply that y value by 2, I would get 4. If I multiply this y value by 2, I stay at 0. So basically you can think of this as if you pull, like maybe this is on a rubber band or something. If you pull that point up here to where the y value is 4, what would the shape do? If we just stretch that up there, the shape would still be a V. It would just be a taller V. Okay? And pretend like that is actually straight as it should be. There we go. Now, this point stayed at 0. If I multiply this y value by 2, it's going to go to negative 8. So this would be negative 6, 7, 8. So this point would come down here to 2, negative 8. And this y value would stay at 0 because when you multiply 0 times 2, you still get 0. So once again, if you can envision just on a stretchy rubber band, if you pulled this point down here but maintained the shape or the general shape, you're just going to get something that looks like this. It just made the graph taller vertically. Okay. That would be a vertical stretch by a factor of 2. Is everybody okay so far? All right. So what do you think will happen on this one? Instead of making it taller, we're going to multiply everything by 1/2, so it will all be shorter, right? Once again, the y values that are zeros will stay at zeros. But when I multiply this value of y by 1/2, it becomes a 1. When I multiply this value by 1/2, negative 4 times 1/2 becomes a negative 2. So it just makes this guy a little bit shorter. Okay. Same basic shapes, just shorter. Questions? Yes? I'm sorry, did somebody say something? Oh, okay, that's fine. No, I thought my headset had wigged out on me there for a second. I wanted to make sure if you guys asked anything, I had heard it. Oh, okay. Oh, I think it's somebody left the building or lost connection. Oh. I think somebody had lost connection. All right. Now, I'm going to give you a couple more seconds to get those drawn, and then we'll do another one. Yes, because we just multiplied by 1/2. That would flip it upside down. So if we had had negative, let me find a different color here. If we had had negative 1/2 of f of x, that would take the 1/2 of f of x and it's going to flip it or reflect it across the x-axis. So this point where it was -2, 2, or -2, 1, sorry, would become -2, -1. So it would just be the mirror image across the x-axis. So that would be there. Put all those together, they kind of make a pretty little picture, but okay. All right. Is everybody okay if we move to the next problem? Are you still copying? Okay. So here comes the big one. We're doing a lot of stuff here. Yes. We are taking this graph, same graph that we had above. We're going to move it right 3. We're going to flip it or reflect it across the x-axis, and then we're going to move it up 1. Okay. Now, there are several ways we could go about this. You can do it in pieces. If we're going to do it in pieces, I'm going to shift it right 3. Then I'm going to reflect it across the x-axis. And then that graph, I'm going to move up 1 unit. And I think that's how they do it in their examples in the book. So that's what I want to look at first. Okay. So let's take care of this one step at the time. So first, we're going to go right 3. Okay. So this point that is at -5, 0, I'm going to move it right 1, 2, 3 units. And that point will be right there. The point at -2, 2, I'm going to move it right 3 units. So that will be 1, 2, 3. And it'll be right here. So I'm just moving every one of these identified points right 3 units. And redrawing my graph. It's the exact same shape. Yes. Exact same shape, just moved right 3 units. That's all I've done to it right now. Is everybody good with that part? I'm sure you're still drawing, so I'm going to give you just a second. There's a lot going on this graph. It was at 4, 0, at 7, yes. 5, 6, yeah, and we're going to call that 7. I may have moved that a little bit too far for my graph paper. Okay. Now, next, just following the order of operations, we're going to take all those y values of my shifted graph and reflect them across the x-axis. So this part, I'm going to do an x-axis reflection. Now I don't go back to my original one. I do the x-axis reflection to this shifted graph. Now if you do an x-axis reflection, any y values that are 0 stay at 0, because if you take the negative of 0, it's still 0. But when it was positive 2, it will now flip down to be negative 2. So this, I know, I gotcha. This V is going to be basically upside down. So that V reflected across the x-axis will look like this. And do the same thing for the parabolic shape. This was at 2, -4, so it will become 2, or sorry, it wasn't 2, now it's 5, but it's at 5, -4, and it will go to that y value being at +4. So that parabola is also going to just flip over the x-axis. Now normally what I would do if I was drawing this for myself is I would probably erase the first translation, because it starts getting so garbled up that it gets hard to see, I think. Would you guys rather me just leave it, or is it okay if I erase that part? I can leave it if you want me to. But if you don't say, I'm going to move it. Okay. Okay. Well, they will be on, they're in your, they'll be in the video, yeah? I'll see what I can do this time. Okay. All right, so this is the x-axis reflection after we've moved it right 3 units, right? And now we want to move every point on that graph up 1 unit. So now we're going to go up 1. So where it's at 0, it's going to be at 1. Where it's at -2, it will be at -1. 0 will go up there to 1. So that little V will just move up 1 unit. Every single point on it's going to move up 1 unit. And the same is true with the parabola shape. So all of these points will just move up 1 unit. So the purple is our final result. Now in a lot of these in your homework, it's going to be a multiple choice type thing where they'll give you several different options for the final result, and you'll have to pick. That is a lot. That is a lot. Now, that's kind of the way they do it in the textbook, except they use, you know, they would redraw the graph several times, you know, and just start. So they would draw the second version of it on a completely separate graph, the third version on a completely separate graph, and so on and so forth. And that does make it a little bit less, you know, kind of garbled, so to speak. But I want to go back up here to this clean version and show you a different way to do that. It's just a different option. Okay, so this is the same graph, right? All right, so let's think about what's going on here. The x values are being moved right 3. The y values are being taken the negative of and then up 1. Okay, so I'm going to start over here. I'm going to move this back up just a little bit so I can get a little bit more on my screen. All right, so I'm going to start with the points that they identified as soon as that comes back into focus. Okay, so the points that they identified were -5, 0, -2, 2, 0, 0, 2, -4, and 4, 0. Those were kind of the key points on this graph, right? Okay, this point, I'm going to move the the x value right 3 units. So what will be that new x value? If I move -5 right 3 units, that's going to be -2. If I move -2 right 3 units, that's going to be 1. Oh, yeah, you were looking at the y. Gotcha. No problem. If I move 0 right 3 units, that's going to be a 3. If I move 2 right 3 units, that's going to be a 5. And if I move 4 right 3 units, that's going to be a 7. So all I've done thus far is move those x values right 3 units. Okay, now I'm going to do the adjustments on the y values. I took the negative of the y values and then I need to move them up 1. The negative of 0 is 0, up 1 is 1. The negative, oh, go ahead. Yeah, it just, but you kind of need to see how it shifts through the different phases, but yeah, I think it makes it a little bit less garbled if you do it this way, but okay, it's fine. If you take the negative of 2, you get -2, up 1 is -1. 0, the negative of it is 0, up 1 is +1. If you take the negative of -4, you get +4, up 1 is 5. This one would be back to 1. So after doing these shifts on this function, my new key points are at -2, 1, 1, -1, 3, 1. So what you have to remember is since we've moved right, these 3 points are the counterpoints, so to speak, of these 3. So that's going to be where your V is. Then we have the point 5, 5 is up here, and 7, 1 would be right here. Those are the points that corresponded to the bits on the parabola, and so that's where our parabola is. And so it's the same thing we got down here, but instead of shifting the graph one bit and then shifting it another and shifting it another, we kind of took the key points and shifted all of them and moved the entire graph at once. But it kind of leaves out the middleman, if you so to speak. And either one is perfectly fine, but it just depends on, you know, your personal preference there. All right. Because it's one of those things that, you know, and I don't know if we'll actually have time to finish this one. So I'm going to go ahead and try to do this one, and then for those of you, if we run out of time and you need to leave, that's perfectly fine. And going back to the question Stephen asked me earlier, I will just go ahead and scan this in today and send it along with the link to the video. All right. Here's my basic graph. We're going to move it left 3, x-axis reflection, down 4. Okay, so what are the, quote, key points that they've identified for us to start? They are -5, 0, -4, 2, -2, 2, 3, -3, and 5, 4. Now notice, guys, when we're drawing these new points, when we've shifted these, they're going to be open circles because those are open circles on the original graph. All right, the x values all need to move 3 units to the left. So to move -5 3 units to the left, that will be negative what? Yes, correct. -4 left 3 units will be -7. -2 left 3 units will be -5, 0, and 2, respectively. Now for the y values, we're doing an x-axis reflection, so we're taking the negative of the y values and then we're subtracting 4. So this y value, if you take its negative, you would get 0, and subtract 4, you get -4. This y value, if you take its negative, so x-axis reflection, the negative of the y value, then you'd subtract 4 and you would get perfect. Here, same thing, you'd get -6. -3, if you take its negative, you will get +3. Subtract 4, you'll get -1. If you take the negative of 4, you get -4, and subtract 4, you will get -8. So our new, quote, key points will be at -8, -4. Let's see, this is -8, -4. -7, -6. 7 would be here. -6 would be here. -5, -6 will be here. Oh, here, sorry. 0, -1, and 2, -8. So keep in mind, pardon me, that all of these little bits were just line segments. So we're going to go with straight line segments between our new points. Except I said straight and then that's not straight, but you get the idea. Questions? All right. You don't have to buy graph paper, but I know it is what I would do if you have the opportunity and have a printer available. There are lots of places you can print off free graph paper off the internet, so that that helps a little bit. But okay, so for Monday, do section 7.2. If you haven't already done 7.3, make sure you get that done, and we will pick up from there. Any questions? All right, well, have a great